Hello everyone. This is a talk about GoPmem, which is the end result of our efforts to add native support for programming persistent memory in Go. I am Mohit, and this work has been done jointly with my colleagues Jerrin, Rajesh, and Pratap at VMware. First, some details about persistent memory or PMEM. PMEM combines the best of RAM and storage devices like SSDs. The read-write latency of PMEM is less than 1 microsecond compared to around 100 nanoseconds for DRAM and tens of microseconds for fast SSDs. PMEM can be accessed with load store instructions and so has byte addressability. The data in PMEM is non-volatile. With all these features, apps running on PMEM can have better performance and instant restart time. In this talk, we present GoPmem, which is an open source extension to Go compiler. It is based on Go 1.11 and supports natively programming PMEM. Applications written using GoPmem outperform the ones written using other solutions. GoPmem has been developed with the intention to merge to official Go distribution. This resulted in minimal changes to the compiler code and the programming model, which is very similar to the existing models. I will now discuss the design goals behind GoPmem. A lot of these are obvious, and we use them all the time today when we write programs operating on volatile data. Programming PMEM should be similar to programming data in volatile memory. And so we will revisit these. First, single type system. Without a single type system, each native type would need an equivalent type which will reside in PMEM. For example, a user who wants to store an integer 10, they would now have to decide the type of 10 based on its location, whether it will be in PMEM or RAM. This is not how today's programs work, so we need a single type system. Support for two heaps. Many programming languages today split the virtual memory into various segments like data, code, stack, heap. In doing so, they already manage a volatile heap residing in RAM. They should be extended to manage a persistent heap. Native pointers. Programming languages which provide access to pointers allow users to get and set data directly using these pointers. So a user can directly do operations like *0x100 equals 1 to set the data residing at address 0x100 to 1. This is important because it provides a fast way to operate on data. Data present in PMEM should be accessible in a similar way, and so we need native pointers. Access PMEM data across restarts. This is an easy one. Because data in PMEM is non-volatile, we need a way to retrieve them after a restart, and this should be easy to do. Crash consistent data updates. This is needed because data in PMEM is non-volatile. Imagine a doubly linked list in PMEM and we are adding a new node. We first update the tail node to point to the new node. And then we update the back pointer from the new node to point to the original list. If all goes well, we get a new node added to the linked list. But what happens if there is a crash before adding the back pointer from the new node, as shown in the second diagram? Now we have a linked list which cannot be traversed in both the directions. So there is inconsistency, and we do not want that. No matter what, we want the addition of a new node to the linked list to be crash consistent, as shown in the first diagram. We want to be able to reuse functions. A lot of our current programming practices rely on abstracting out operations as functions and reusing them from different places. We want something similar. We don't want to rewrite functions which do the same thing, only for data residing in pmem. So if we have a function, irrespective of the location of its arguments, whether it is in DRAM or pmem, the function should just work. We want the flexibility to make pmem updates anywhere in our programs. As I went over before, we want data updates in pmem to be crash consistent. And one way to do this is through transactions. But transactions have overheads. For example, in an undo transaction, all the updates are made in place. But before an in-place update, the old data is copied over first. This degrades the performance of updates. If we go back to our previous example of a doubly linked list, a user may want to create a new doubly linked list in pmem and change the head pointer to point to this new list. With the flexibility to make pmem updates outside transactions, user can create all the nodes in this new linked list outside a transaction and then atomically switch the head pointer. This kind of flexibility also augurs well with techniques like shadow paging, typically used in database applications to avoid transactional overheads. With all the design goals behind us, here is a program written in GoPmem. This program adds a new node to the tail of a doubly linked list. We will now look at each line and see what happens. We want to highlight that this is very similar to existing Go semantics. First off, we are creating a new node in pmem using the GoPmem keyword pnew. This is a language change. We have added two pmem allocation APIs in GoPmem. pnew allocates zero-valued objects similar to the existing Go keyword new. pmake allocates zero-valued Go slices in pmem. Slices are an integral part of Go language and can be thought of as an equivalent to C++ vectors. txn is a GoPmem keyword to demarcate transaction boundaries. Internally, it implements undo logging. We support calling functions as we show here with the update tail function. We also support most Go statements inside txn block. Expanding a bit more, transactions in GoPmem are the way to make crash consistent updates. These transactions support all the ACID properties. I will not talk more about how we solve the problem of isolation in GoPmem transactions. GoPmem transactions can be used by multiple threads to make updates to data in pmem. Imagine three threads accessing the tail of a doubly linked list. One of them is updating the tail to point to a new node, and others are reading the tail value. Because GoPmem's transactions are undo transactions, all the updates are in place. So the first thread updates tail to its new value of 0x200, and this update is in place. At this point, even though tail contains the new value, the transaction is not over yet and can be potentially reverted. So no threads in the system should be able to see tail equals 0x200 until the transaction is successfully completed. We provide isolation in GoPmem transactions by requiring users to use Go mutex. Mutexes are already a tool to provide isolation for critical sections. GoPmem builds on this. The concurrency model has two simple rules. If a mutex was acquired outside the transaction, it should be released outside the transaction. The isolation in this case is natural because the transaction is inside the critical section. If a mutex was acquired within a transaction, it should be released within the transaction. GoPmem provides isolation in this case by delaying mutex unlocks until the transaction is successfully over. For a more detailed explanation and limitations of this approach, please refer to our paper. Now Jerrin will walk you through the rest of the content.
We provide various pmem APIs to help users with pmem initialization and restart. First, the init API is used to initialize GoPmem. It takes a file as input and returns whether this is a first-time initialization or not. If this is not a first-time initialization, it also takes care of reverting any incomplete transactions. Next, named object is a mechanism whereby names can be associated with objects in persistent memory. The new and get APIs, respectively, can be used to create and retrieve objects in persistent memory. For example, the code snippet shows creating and retrieving a named object called head, depending on if it is a first-time initialization or not. So to summarize, we highlight how our programming model achieves all the design goals that we mentioned. Line 2 shows a new node created using pnew. GoPmem uses a single type system, so object n has the same pointer type as objects in volatile heap 2. GoPmem runtime automatically manages both the pmem and volatile heap. GoPmem also support pmem updates outside transactions to objects that are not reachable from a named object. The third line in the code snippet shows how the txn keyword enables crash-consistent data updates. GoPmem uses native pointers, but offers features such as heap relocation that I will talk about later. Line 5 shows a pmem pointer update. Pmem pointers can be accessed and modified just like volatile memory pointers. Line 6 shows a function used inside a txn block. Functions in GoPmem can be called with volatile and persistent memory arguments. Additional overhead to enable crash-consistent updates are incurred only for pmem resident arguments. GoPmem provides easy access to pmem data after a restart. Line 20 and 22 shows how a named object can be created and retrieved. Now I'll talk about the runtime design that provide the building blocks upon which the features of GoPmem are based on. First, GoPmem provides a pmem heap and enables memory allocation and garbage collection on the pmem heap. The pmem heap is dynamically sized. Applications start with a small heap that is expanded on demand. Pointer swizzling is a powerful feature that enables GoPmem use native pointers. GoPmem provides a heap recovery mechanism. This is what enables applications to run seamlessly across a crash and restart. The runtime also provides CPU cache flushing support to ensure durability of data. I'll go into the details of few of these aspects in the upcoming slides. GoPmem extends the existing Go memory allocator design to manage pmem heap. Pmem is managed in arenas that are a multiple of 64 MB. It should be noted that all data structures used to manage the pmem heap is stored in volatile memory. But Additional metadata is stored in the header of each arena to facilitate heap recovery. The additional metadata occupies about 3.1% of the arena space. GoPmem enables applications to use pmem by mapping the pmem file into its address space. But what happens if the mapping address changes after application restart? Here, the first figure shows the pmem file mapped at address 100 during its first run. In the second run, the pmem file gets mapped at address 200. Now, all stored pointers in the heap are invalid. For example, the pointer that was pointing to address 110 now becomes a dangling pointer. Pointer swizzling is a process by which the runtime fixes up these pointers in case the mapping address changes. Pointers are swizzled automatically during pmem initialization. To fix the dangling pointer, Go runtime changes it to point it to address 210, which is the correct swizzled address for it. Pointer swizzling enables GoPmem to use native pointers to refer pmem objects. Heap recovery is a process by which the memory allocator and garbage collector state is recovered in case of an application restart. First, using the stored metadata in pmem arenas, the memory allocator volatile state is restored. Next, if the memory mapping address changes, then all stored pointers are swizzled. Next, the garbage collector is run starting from the named objects. The garbage collector traverses all reachable objects and plugs any leaked memory. All steps in the heap recovery process is resilient to any crashes that happen in between. Once the heap is recovered and any incomplete transactions are reverted, the application can resume execution. A question that is frequently asked is why not provide pmem support as a Go package, and why is native language changes necessary? There are a few reasons why. With a library, memory management becomes tricky. It wouldn't be possible to leverage the existing memory allocator or garbage collector design provided by Go, as it is tightly coupled with the runtime and not accessible from a library. Libraries will need to introduce their own management of pmem data, such as doing reference counting, which can get tricky. The programming model would get complicated. It would no longer be possible to use native types and pointers. Operators and pointers may need to be overloaded to provide functionalities such as transactional semantics. Programming languages have already been managing volatile memory for many years now. We argue VMware, which is another type of memory, should also be managed by programming languages. As I will talk about next, our evaluations also prove that our effort to add native support performs much better than the other pmem libraries. To evaluate GoPmem, we ask two important questions. Do my applications run faster with pmem? And do my application restart faster after a crash? We developed a Redis server called go-redis-pmem to understand how a real-world application can benefit from GoPmem. We also use benchmarks from the computer language benchmarking to perform micro benchmarks of our memory allocator and transactions. We compare against other pmem libraries such as PMDK, Makalu, and Nemosini. First, we compare performance of go-redis-pmem against two other Redis implementations. PMDK Redis, which is a Redis server written using PMDK library, and Vanilla Redis, which is the original C implementation of Redis that stores its log files on SSD that is labeled as C Redis SSD in the figure, and on pmem used as block IO labeled as pmem block IO. As can be seen in the first graph, Go-Redis pmem achieves 5x more throughput than C-Redis SSD as the data size increases. The second graph compares the restart time. Go-Redis pmem comes back up 20 times faster than C-Redis SSD when the database size is 3 GB. This graph also captures the cost of pointer swizzling. When pointers need to be swizzled, Go-Redis pmem takes as much time as C-Redis SSD. But pointers need to be swizzled only when an application restarts and the mapping address changes, the combination of which happens rarely. We use the binary tree benchmark from the CLPG suite to compare performance of our memory allocator. The benchmark creates a number of binary trees and frees them to stress the allocator. As seen in the graph, GoPmem's allocator performs up to 40x faster than PMDK and MemoSini. Memory allocations need to be transactional in PMDK and MemoSini. GoPmem and Makalu optimizes allocations by not updating any metadata in PMem in the common case, making them very fast. Next, we use the Farncuch and N-body benchmarks from CLPG to evaluate performance of transactions. Farncuch benchmark swaps elements of an array for all permutations of the array and models a long-running transaction. N-body traces single-step movement of a planet across space and models a short-running transaction. For both these benchmarks, GoPmem performs up to 5x faster than PMDK. To summarize, GoPmem is an open source compiler that provides native support for programming PMem. We have created a website from which you can download GoPmem and start using it right away. It also has additional documentation and performance reports. I would like to close with a call to action. Persistent memory DIMMs are now available with the release of Intel Optane PMem. Our immediate next steps are to look into upstreaming our changes to Go. So we welcome suggestions and feedback from the community to help with that effort. PMem makes it possible to build low latency storage stacks. With the availability of both hardware and software support to program PMem, we implore you to build the next low latency applications such as time series databases and those at edge devices using persistent memory. Thank you for listening to this talk.